I have planned to teach Haskell with recursion, right? So Haskell being a functional programming language is suitable to learn about recursive algorithms, right, which are typically seen as hard problems, right, in most DSA courses. But with respect, but through learning Haskell, these problems could be learned in a natural way, natural intuitive way, right? So how to install Haskell? So GSC Cup is the main Haskell installer, right? So you can install for your respective operating systems by visiting this website, right? So after you get this installed, you can complete your setup in Visual Studio Code. You can install the necessary extensions you want, right? So I have my Haskell extensions installed, right? So you can do the same. All right. So let's get started. So this GSCI, right? So this is called the Glasgow Haskell interpreter, right? So Haskell is a compiled programming language, but it ships with an interpreter, right? And it's really handy to start working with it. For example, you can multiply two numbers. So this is very similar to any programming language. You can add two numbers also, but you will soon realize the problem when you try to divide the numbers, right? So this division, it is happening. I mean, this division is applied as a float number, floating point division. Okay. So what to do if you want to get integer division, right? For example, in C, if you divide two integers like 7 divided by 5, you'll probably get the answer just 1, right? So how to get that kind of division in Haskell? So in order to get those kind of results, you have to use a function called div. So div is a function defined in Haskell, right? So 7 5, you will get this answer 1. Right, this is for used for integer division. In Python, you will use this double slash operator to divide two integers, right, to get the integer division, but this is not defined in Haskell. Okay, so these div and all these functions, so all these things will come from this package called Prelude. So this Prelude package is kind of like the base package, right? So it comes with most of the inbuilt functions that ships with the compiler itself, right? So yeah, so if you want to really look at the type definition of these functions, you have to use this type command. So if any command, I mean, if you type into GSCI with a colon in the beginning, it means that you are typing in some command. So these are not uh, the usual thing that you will write in your programs in a file, right? But this is a handy command which will tell you what kind of function it is, right? So these syntax might look strange to you. So what this really means is that it takes two parameters as input, right? And it returns an output. And there is a constraint. So this has to be read as a constraint. This constraint, it says that this A should be of an integral type. So integral type, okay, why it is specified as an integral type? Because it either has to satisfy integers, and so these things are called type classes, right? So these are very advanced topics, and I don't think it will be good to dive into this topic in the very first class of you learning Haskell. All right, but anyway, let me give a slightly more introductory topics. Right? Let's start with introduction.hs. Right, module introduction var. Okay, so this means what does this module keyword specifies? It specifies that whatever the functions that we write in this particular file can be reused anywhere from other files, right? So if I remove this, then that won't be possible. Okay, so I can just simply start writing it as here, but it is better to write in this using this definition. Okay, so one of the basic data structure provided with Haskell is the list, right? So this is a singly linked list. singly linked list with a single pointer at the head. Okay. So how to create a list? For example, I can create an element like xs, some list elements 1, 2, 3, 4. This is allowed. So this is a list of 4 elements. Okay. And if I want to, let's see, let's write a function to find the length of a list. Okay, so it takes a list as an input and it returns an integer, let's say an int type as an output. Let's write integer. Okay, it returns an integer as output. Okay, so what does this a means is, this a means it can be of any type. So this is called a type variable. I can put the name b here. It doesn't make any difference. I can put just b here, whatever I want. The essence is that it's a type variable. So how to define this? So we use something called a pattern matching. So if it is an empty list, it will return the length of the empty list is 0, right? So if it is a non-empty list, then how does it looks like? It looks something like it has at least one element, right? And the rest of the elements. So I should write 1 plus len of xs. So this is defined as a recursion, right? So we compute the length function by calling the length function on a smaller list. So this colon operator is called the cons operator. This is like a constructor for list. I will explain this how it works. So for example, list of 1, 2, 3 is equal to 1 colon 2, 3. No. Right? This is true. Both of them are same. Okay. For example, if you see 1 constructed by 2, 3, you will get the list of 1, 2, 3. So this is how you do pattern matching, right? And there are other handy list operations. So if I say list, I mean x is equal to list of 1, 2, 3, 4. What is head of this list? This the first element 1. So what is tail of this list? It is all. It is a list except the head element. Okay. So this is how pattern matching works, right? So let's take a look. Like how will you write this code in Python? In Python, if you want to find the length, you will define a function like def len. It takes an input. Let's call it axs, right? So you will. I mean, Python list is inbuilt, and all those functions. I mean, it will be. It's an object-oriented programming language, right? So the problem with comparing Haskell with Python is that all the methods to work with the data will be shipped inside the data itself. You will do the list dot length. Give me the length of the list. You will ask to that object itself. So in Haskell is a functional programming language. You cannot poke into the data. A data is simply a data, right? And you have to write functions on top of it. Okay, so this is a completely different way of viewing about programming. Any doubts so far? Please speak. Don't write it in the chat. Okay, so all right. So I believe that this pattern matching syntax is much more. It looks closer to a pseudocode, but it's like a precise pseudocode, right? And this code, it actually works. It can Haskell runs in production. Haskell has been used by in many companies like Facebook. In Facebook, in early stages, they started using Haskell for parsing the websites and all the other stuffs. And many new programming languages are being written in Haskell. Okay, but thing is that it is not very popular. The reason it is not very popular is because of, I believe it is due to the community, right? The community is comprised of mostly mathematicians. Even I am a mathematics student, right? And yeah, we are not so popular, right? So mathematicians are not so popular, and that's why it's not so popular. But the thing is that it is slowly gaining traction and it's slowly influencing all the other programming languages. For example, since Java 2008, right? Since 2014, right? Since 2014, let's talk about Java 8. Almost all features that are being included in Java are somewhat inspired by, or mostly, let's call it, or mostly inspired by YAML based languages, YAML based programming languages. Okay. What are the YAML based? YAML is here does not stand for machine learning. It stands for like YAML is a, I mean, specification. It's a functional language specification, right? So you have the languages like OCaml, even Haskell is derived from yeah, standard ML, right? So, but the thing is that Haskell is a lazy programming language. Lazy in the sense the evaluation is done when it is needed. It is not strictly evaluated. But yeah, so this is also a little bit advanced topic. Let's not dive into this too much. Okay. All right. So now I want to create a function. All right. So which can create all possible subsets, right, of a list, something like that. Okay. No, let's do a simple function first. First of all, let's write a function which creates all possible permutations of a list, right? Let's call this permutations. Okay. It takes a list and it returns a list of all possible permutations. The permutations of an empty list should be, let's call it empty of empty list, right? Or it should be an error. I believe it should be an error because there is no way to arrange an empty list. Maybe, not sure, but let's stick with it. So permutations of a single element, right? So this is how you specify a singleton list, right? Singleton list is just the list of, it has only exactly one permutation, right? But permutations of zero factorial is defined. Since zero factorial is defined, I believe we can, rather than throwing error, we can simply write empty of empty list, because zero factorial is also one, right? And since we have already defined the base case, let's not worry too much about. Let's just go with this. We don't have to specifically write for the singleton case, right? Because we have already handled the base case here. Okay. So what I am going to do is, first of all, I'm going to use something called a let expression. I'm going to say let rest of the permutations is equal to permutations of xs. So what I'm doing is I'm just creating I'm recursively calling the permutations function on the remaining rest of the elements, right? So this let expression means it binds a computation, a result, to a variable name. Okay. So after creating the list of permutations of the rest of the elements, what we'll do, we can regenerate all these permutations. So let me just explain in pseudocode how this algorithm works, right? So this will become very clear. So if you want to create the permutations, let's say the permutations of the list of elements 1, 2, 3, what I will do is first I will solve this problem by creating the permutations of 2, 3, right? So let's say that the permutations of 2, 3 we already know. That's very simple. We can write 2, 2, 3, 3, 2. Right? So let me just store this result in a variable called rest. Let's say it as rest. Let's store it as rest. So then what I will do, I'll take this permutation first, right? And with this permutation and with this particular element 1, I can create 3 different permutations. How? I can create 1, 2, 3. So this is 1. And then I can put 1 in between 2 and 3. 2, 3, right? Then I can put, 2, 1, 3. Then I can put 1 at the end. 2, 2, 3, 1. And similarly, I can create 3 more permutations by inserting 1 at every single position in the rest of this thing, right? So that's exactly what we are going to do here. Okay. So this rest, first of all, what will be the type of this variable? This will be a list of list. Why? Because permutations, it takes a list and it returns a list of list. Okay. So here also we have that only, right? So permutations of 2, 3 will be a list of list. And for each list, we have to create the respective corresponding permutations. Okay. So let me just so how to do that, right? So here we have a list of list, and for I mean this is a very small example, but in general there could be multiple results, right? And we have to combine all those lists together. All right. Let's see. I mean, let me just have it as a error not implemented here right now, because in order to do this, we have to implement like many helper, small helper functions, right? So how to concatenate two lists in Haskell? There is inbuilt operator actually available. We can write 1, 2, 3 plus let's say 4, 5. You'll just concatenate these two lists, right? But let's try to implement this, implement that by ourselves, right? So this is an already inbuilt function, right? So let me just write concat list, right? It takes a list of elements of type A and list of elements of type A and returns a list of elements of type A by concatenating both of them, right? So we can use pattern matching to make this simpler, right? So if the first argument is an empty list and whatever the second argument is, I'll just return the second argument. But if the first argument is non-empty, right? And if I get the second argument, then how will I express this, right? So this is, I mean, first of all, you have to understand this X is an element. It's an element of type A. A is any type variable. We can have a list of integer, list of strings, or list of any user-defined types, right? So what I'm going to say is concat the tail with the other list, right? And I'll write something like this, right? So uh, uh, I mean, put X at the beginning, right, of concat list xs ys, right? Like I said, it's a singly linked list, right? So this is, I mean, you can think of this colon operator as a link, okay? And as I said, this head is the head pointer usually points to the first element, and if you say tail, you get the rest of the elements. But here you don't think in terms of pointers, but I'm just using the word pointers because most of you coming from other programming languages should be familiar with that term, right? Any doubts?
No.
Right. So far so good. So this is how you can we concatenate two lists, right? So, but before we understood that in order to implement this algorithm, we need to concatenate two lists. So that's a requirement. But we also need to put, let's say, insert one element in all possible positions of the list. That's also need, right? So let's do that. So insert, how can we name that function? And let's call it all placements, right? Whatever, all placements. It takes a single element of type A, and the rest of the lists, right? Lists, and it returns a list of lists by making all possible placements, right? So all placements. So you have an element x and xs. So as we can see, we need to place it in the beginning and in front and in the first, like in how many places we have to place it. We ideally don't want to use the length function. I'm thinking whether we can create one more simplified function to make our life easier, right? So we can ideally place it in the beginning. That would be very easy, right? So we can uh, make the placement obviously in the beginning, right? And then we have to make the placement in all possible positions.
Don't we have loop kind of loop variants in Haskell? Like
No,
we
we don't have loop. We essentially have to use
we
recursion for loop. So
okay.
here also that's what happening. See, not to find the length, we are using recursion to essentially do the looping variant. Right? Because when you think about loops, see, if you are introducing looping constructs in your programming language, then what does it mean? It means that you are giving low level control to the programmer, right? So you should expect uh, index out of range errors, right? So you should expect index out of range errors and all those other variants. So we can simplify this problem. So rather than trying to do all placements, okay. First, let's try to do a single placement, right? Place in position, whatever, place in some position, right? So you get a position based on integer or whatever integer, right? And then you have a list, and then you take an element, then you take a list, and then you return a list. I'm going to place it in a particular position. Okay. So this also I'm going to implement using recursion, right? So here I'm going to put this element little bit in front. You will understand why I did that. Okay. So place in positions, we have to put this element x, right? So if it is in the 0th position, okay, I will just return x. I'll just put the x in the beginning, right? Else what will I do? Place in position. Uh, yeah, but here we have to consider other cases as well, right? So if x, whatever the number is, n, when which is greater than 0, right? And we get a empty list. Okay, so how to handle this? This should be an error. Why this should be an error? Because in empty list you can only put the element in the first position, that 0th index. right? There is no way talking about put it in the first or second position because there are already no elements in the list, right? Whatever the element that's going into the empty list, it should be in the first position, right? So you are using zero base indexing, let's say that, right? Error index out of bound. Okay, we are throwing an error, right? So place in position x some integer and it is a non-empty list. Let's call it ys. Right? It's called yxs. It doesn't matter. Okay. So now what I will do, I will recursively call place in position the same element, but I will pass n minus 1, right? And the rest of the. So placing this element in the nth position of this list, this entire thing is a list of this list, is equivalent to taking the head element of this list and putting in the beginning and placing this element in the n minus 1th position of the tail of that list. So that's exactly what I'm doing. Right? Any doubts so far?
No. Yeah.
Okay. So now with respect to all placements, right? Okay, let's do one base indexing itself. Or one, yeah. Or one or zero. No, let's do zero because zero is most convenient. Okay. All right. And now, so what are the all possible positions that we can get for this list, right? So here, if you look at it, so there is a 0th position, which is in the beginning. There is a 1th position, which is in between. I mean, within the index 1, and there is the index 2 position, right? So from 0 till length of this list, we have to uh, like enumerate all possible positions. Okay. And there is an elegant way of doing this by using kind of a comprehension for comprehension kind of things. It looks very similar to or mathematical notation that we use, but it comes from the concept called monads, right? But they are, so that's a very, let's say, I mean, it's actually pretty simple, but it kind of it can look very alien to us, right? So I observe carefully, right? So I'm going to place in position, right? And I'm going to place this particular element x, right? This element x. Then I'm going to take this variable n. We still have not defined this variable n so far. And the rest of the elements x's. And I'm going to use this syntax, right? Like it reads like such that in mathematics, right? So given this condition, if you're familiar with the set roster notation in mathematics, right, it's exactly the same. Okay. And n, I take it from 0 to, so we have already defined the length variable, length function, right? 0 to len of xs. So this is another handy notation provided by Haskell for to work with list. For example, if I say 0 to 2, it it gives you the list 0, 1, 2, 2, like two dots, not 3 dots. So if I say 1 dot dot 100, it gives you all the elements from 1 till 100. So it's inclusive. Both of them are inclusive, right? Okay. So you probably get all possible placements. All right. So now we have defined this simple function also. So just observe how we are solving a problem. We are solving a bigger problem by simplifying into smaller problems, right? We are creating smaller and smaller functions. So even by the design, how we design the programs, that itself is based on recursion, right? So that's why Haskell is a very good language to learn about recursion, right? It completely changes the way you think. Even looping is done through recursion. So you will get pretty comfortable working with recursion, right? So now you should get idea on how to solve this problem, like we discussed, right? So first of all, first we will create the permutations of the rest of the elements, right? And then we will once again we will use the same notation. Okay, I will say all placements, right? I'll call this function for this particular element x first, right? So for this particular element x, for example, 1, 2, 3, if you observe it, we call the recursion on the rest of the elements, and we will place 1 in all possible placements on the rest of the results, right? X permutation, let's call it that, permutation, such that permutation is taken from the rest of the elements. Okay. Yeah, it's showing the error. Why it's showing the error? Because there's all possible placements. If you put x into it, so this itself is a list of list, right? And again, I'm calling. I'm trying to call this. Okay, we will define. Let's create one more function called concatenate lists. Let's just call concat lists, plural, right? So what we will do, we will have a list of list, and we will return a list, right? So first of all, observe this, like, to pay close attention, right? This element a, it could even be a list, because a list is a type, right? So this a is a variable, it can represent any type, right? So this result a here, this a, it could even be a list of list, right? So that's what we are thinking in terms. I mean, Haskell provides you the tools to write the program in such an abstract way, right? So you can you can write programs like the same way you write mathematical proofs, but it will be very precise. You can write very precise programs. Okay, so concat list of an empty list is just a list. Okay, so now concat list of, you have a list of xs. This xs itself is a list of list. So what I will do, I'll call concat list function, which we have already implemented. So that's why I will write it in this way. So xs represents a list, x double s represents a list of list, right? And I will call concat list on the remaining, concat list on the rest of the items. Okay. Let me explain how this works, right? For example, if we have a function of, f is just a shorthand notation for this function concat list, right? So concat list of 1 comma, we have a list of list, right? So let's say 1 comma 2 comma 1 comma 2, and here comma singleton list 3. So what I'm doing, I'm calling, and let's C denotes the concat list function. Let G denote the concat list function. Okay, I'm calling G of list of 1 comma 2 and F of list of XSS, right? So yeah, list of 3. Okay, and how does this F of list of 3 where it will get simplified as list of 3 into it will g of g is the for concatenate list, right? So this function is g of list of 3, f of empty list. And we all know that this f of empty of empty list is just an empty list, right? So we can just rewrite it as empty list. And concatenating g with this list with the empty list, it should be an empty a singleton list 3, right? So this equation, it simplifies as a singleton list 3. So this equation can be written as g of 1 comma 2 and this list a singleton list 3. And as we know, this concat list of two lists should return the value 1 comma 2 comma 3. So as you can see, writing programs in this way allows you to reason equational. It allows equational reasoning, right? The same way that you do in mathematics. So if you write the same program in other programming languages like Python or Java or C by using loops and all, you cannot do this equational reasoning. Of course, you can use like techniques like loop invariance to reason about those concepts, right? But this equational reasoning by substitution, I'm essentially substituting like the equation, right? So these kind of reasoning is not possible in like the procedural languages. Even Python and Java, they are procedural for most part, right? They have object oriented programming features, but when you try to implement something in particular, you're probably going to use procedural constructs, right? Yeah. So that's why it is showing an error. So let's read this error. Couldn't match expect type A with A of list of A. I mean, the expected result is a list of A, but the actual is list of A. Right? Why? Because we want list of A, but it is complaining that you are giving list of A. The the reason is what we are ending up at the as a whole is list of A, right? See, if we have one outer list expression, right? This outer list expression we have. So whatever the inside, it should be a list of A. It should not be list of A. Okay, so that's why it's saying the expected is list of A. So whatever is inside this outer list expression should be a list of A, as you can see. But the actual thing that we are getting is list of A. So what we are supposed to do? We are supposed to concat lists, right? So now what is happening? Yeah, this is spelling mistake. Invitation. Yeah, now this should be fine. Okay. So now let's get back to our REPL, right? GSAI, and let's try to load these functions, right? So let's load. So load. I mean, this stands for load command, but let me just write it in this way, right? Even this works. Even the shorthand notation L works, right? And we can let's try to work with our list length function. Like length of empty list is 0 as expected, singleton list is 0. Let's say 1 1 1 1. Let's put 5 elements, 3 4 5, so the length is 5. So this is working as expected, right? So let's test our concat list function. Concat list 2 comma 3 4 comma 5, yeah, working as expected, right? So let's try to test the edge cases. Empty list, another empty list, yeah, working. Let's say 5 comma 6 comma 7, yes, working as expected, right? Yeah, duplicates is also working as expected. So place in position, right? So I can create a new function called place one by specifying a single argument here. Place in position, not in scope. I think I made, yeah, the spelling mistake, yeah, right? So you can ask me what it is. What does place one means? Okay, so it's now there is showing that it cannot print a function. The printing of function is not defined, but I can use this type command, right? Place one. Okay, so it expects a number a integer because it is placing, right? Yeah. So what is the type of place in position? This is a function that we have defined, right? So it just gives us the function signature, right? Or function signature as it is. So what I have done is uh, I wrote like play. Okay, so that was deleted. Okay, so I write place one is equal to place in position one. So I have supplied this one a single argument to a function which accepts one, two, three arguments. Why this is allowed? So the idea is that in Haskell, every function accepts only one argument. Okay, but you can say, but this function it accepts three arguments, right? How can you say it accepts only one argument? Because there is a concept called currying. Currying in the sense, so this function will be treated as a function which accepts a single argument and which returns a function. This can be read like that, read in that way, right? So it takes a single argument and it returns another function which takes two arguments and returns result. And and even this can be considered as a function which takes a single argument and returns a function which accepts a list and returns a list, right? So this feature is called currying. Okay, and this is not available in most programming languages like Java, I mean, like object-oriented programming languages like Java, C++, and so on. But in Scala, this is available to a certain extent, right? And even in Python, you can import a library to achieve this. So now you can see how Haskell is influencing other programming languages, right? I mean, not exactly Haskell, this YAML, right? Because Haskell is inspired by YAML, let's say that. Okay, so so if you Google currying in Python, right? So this feature is actually available in Python. Okay, so you have to import some specific library, I believe. Yeah, you can write it in this way, but yeah, but there is a library. Yeah, yeah, from Func Tools, right? There is a library called partial. So from there you can import Func Tools, and this Func Tools allows you to do this, achieve the same thing, same currying effect, right? So you can read about this. Okay, but in general, this is especially used in data science, as I can see. Why it is used in data science, right? That's a good question. Because in data science, like you often want to create a function by applying some specific arguments. The idea is you don't have all the results, like all the data with you all the time, but there is something called like streaming problems, right? But I'm not exactly sure about it, but I know that it has been used in Python also. Okay, so where are we? We were testing functions, right? Yeah, place once, and let's test this place one function. Okay, so I can call place one, right? So what's a place one? This is a function which takes an integer and a list, right? So let's try to place in the index 2 for the list 1 comma 2 comma 3, right? So as you can see, it places in the index 2. So this 0 1 2, right? This element 1, or else I can write like this. So this will be much more obvious. 5 4 6 3. Yeah, it places in the index 2, places 1 in the index 2, and let's say place 1 in index 0. This does. Place 1 in index 3. It does at the element right last. But if I say place 1 in index 4, it should throw an error. Right? We get a stack error called at introduction displays, right? Index out of bound error, which is exactly what we have wrote here, right? Okay. So now let's call all placements functions. All placements we want to apply one, let's say on this list 2 3, Okay, so it is returning all the placements, applying one at the beginning, then at the second position, and at the third position. Let's test it for 3 2, right? So here also we are getting all the expected results like I have described here, right? Great. So now let's create the permutations. Let's test our permutations. Let's say create all permutations from 1 to 4, right? Non-exhaustive pattern search. So there was a certain mistake in our code, right? It's saying non-exhaustive pattern search. Okay, let's test this simply. Let's For empty list we are getting empty list. Okay, okay. Here is the concat list. I believe this is because we did not handle the singleton case properly, and that is allowing. I mean, since we did not handle this, we were getting it. I mean, let's investigate it later. Let's reload it. So this R stands for reload. So I can is a shorthand form for this command, reload command. Okay, and now let's call this permutations. Now we should return. Now let's say permutations 1 2. Okay, still we are having non-exhaustive pattern search error in concat list. Okay, so in function concat list. So it's not due to this pattern search. So here we have, so here the base case is obviously not handled properly. Okay, so yeah, it should have been this. Yeah, right. Because yeah, so that was a silly mistake by me. Yeah, so we are getting permutations 1 2 and 2 3. Let's say 1 2 3 1 2 3 2 1 3 2 3 1, and all the permutations as expected. Then 1 to 4, right? So we are getting as expected. 1 to 10, I believe we can get the results shortly. Yeah, it has finished computing and it is just printing it, or else it did not. It's just, since it is lazy language, even before finishing the computation it can print. That's what I think, but not sure. But it's a very large number, right? 10 factorial. Stop it, right? Because let's see what 10 factorial is. 10 factorial. Yeah, it's a big number, and it is trying to print, right? So that's why it's pretty slow. I believe if you can create the factorial function like this, let's create a factorial function and let's see if it computes faster. Right? Factorial n factorial of 0 is equal to 1. Factorial of n is equal to 1 and 2 fact of n minus 1. Okay, and as you can see, it is not required to manually annotate the function signatures, even though that is suggested. But Haskell has something called type inference. So the types of the functions will be deduced from whatever the operations that we are using and how we are calling that function. Okay, but still, let's just reload this. So let's call factorial of 10. No, not 1 into, sorry, n into. Right, yeah, this function is pretty, this will get compute, but let's reload this. Let's call fact of 10, right? But let's try to create all these elements. So even this should compute faster, I believe, but still it's taking time. See, so that's why, as you can see, why it takes so much time to print all the elements, right? Anyway, it's a very big number, but with permutations of 1 to 5, I think this should complete fairly quickly. Yeah, 1 to 6, yes. 1 to 7, also yes. But 1 to 8, it takes some time, whatever. Okay, but what have we learned today, right? So we learned how about essentially lists. right? And recursion. So why are we using list for recursion? Because list itself is a recursive data structure, right? The head element and the tail element of the list itself is a list, right? So it's a smaller list anyway, so that's why it's a recursive, right? So it divides into smaller problems. And we learned how to concatenate two lists using recursion, to find the length of the list using recursion, right? And concatenating list of list using recursion. And here I made a silly mistake by specifying the base case as a singleton list with empty list, right? So that was a silly mistake. Okay, the base case is just an empty list, because the base case of list is also an empty list, right? So we learned, I mean, we created another function, right, to simulate the. Why did we create this function? We created this function to simulate what? To simulate looping construction, right? So we want to place in some particular positions, right, from 0 to this len of x's. So in a particular index, we want to place this element x on the list x's. So we did that exactly, and that even that is using recursion, right? So in a typical programming language like Python, you would have used a loop, but here the loop constructs are not available. All right, so here we created this all placements function, and here we use the list comprehension to generate all possible uh, indices from 0 to length of x's, right? And we did the placement as explained here. And from all these smaller functions, we implemented this permutations function, right? This is the main function that we want to do in a single line. Okay, in a single line, we wrote this permutations function by composing smaller functions. Okay, so this is one smaller function, right? And here this list comprehension is also kind of a function, right? And this all placements is another smaller function, and this concat list is also another function. So essentially we are building like a Lego blocks, a bigger program we are building with smaller programs, and we are doing this composition pretty effectively, right? So yes, so building bigger programs from smaller programs, that's exactly what recursion is, right? So solving a bigger problem by solving the smaller problem first, and that's what dynamic programming is also about. So writing program in Haskell, you will get comfortable with recursion a lot. That's exactly the concept, right? So any doubts, anything you want me to look in particular right now?
No, all clear.
All clear, right? So yeah, so I mean, so let's make this clear for the audience, right? So this is the first time I believe you are learning about Haskell, right? How does the code looks? Whether the code looks like so confusing or alien or what?
A bit confusing,
Yeah,
but
I think the one thing that confuses you a lot is how we call functions. We don't use brackets to call functions, right? We use like separations, a space as a separation. So that is one confusing thing for beginners, right? So because concatenation is also a function, right? And we are supplying the arguments by specifying spaces, right? So that's even for the length, as you can see, we don't we, if we try to do this length of x's, it will throw an error.
and this is also quite confusing. I am not sure whether that is a return type. So
Yeah, there is no return keyword. As I said, it's equations. You write equations.
okay. So what is that? So line 23. So you have created a concat list, and then A.
So this is like
Which
function signature,
okay? What
type
does it mean?
signature.
The right hand side A.
Yeah, as I said, it's a type variable.
Okay. Then again, why you have written? So what
Yeah,
is
because it takes two lists of same type. That's what it means. And it returns the list of that same particular type.
okay? But in line 36, it takes
An
uh
element A
which is of type
and
integer.
type A, whatever. Now, element A could be of any type, and then
It
one integer, right? And this list should also be of type A. See, this is what Haskell allows you to write expressive programs, right? It allows you to write polymorphic code. Okay, so if you want to do this in C or Java, it's not so simple. You have to resort to generics and so on, right? In C++ and Java. Python is not a type programming language. You don't specify type like statically, right? But if you look at C++ or Java, you specify type statically for most part, right? There you will resort to something like generics to do type constraints and so everything. If you use object everywhere in the type signature in Java, what will happen? There will be no type checking. Here there is type checking happening. Okay, how type checking is happening? Let me show you an example, right? So if I do concat list of list of 1 comma 2 comma 3, and if I pass a string like 1 comma 2, it will throw an error. It's saying that both the list should be of the same type, right? No instance of num string arising from the literal one, because here it is a string, right? And here it is a number. 1 to 3 are considered as a number type, right? So this num is also type class, right? So but what you have to like observe is that in line number 23 there is a constraint on what input that you can provide. Both of the arguments should be of same type, right? So this will throw an error, but I can do this concat list 1 comma let's say 2, and I can supply another argument 3 comma 4. This is allowed, right? Concat list. So you are getting generic code. So I did not write concat list for a list of numbers first and then a list of string first. I just wrote one code, right? And the compiler, Haskell compiler, is smart enough to generate the code for other all the possible types, right? So that we call. So if I can do this for 4 comma 5. So this is allowed. Sorry, 4 comma 5. Yeah, this is allowed, right? So you are getting polymorphism and you are getting type checking also. Okay, and that's for this is all the same thing only. You have to return a list of type A, otherwise the code won't even compile, right? So the input, you have a list of A, and the output should be list of A. This A is a type variable. It usually means that it can be of any type, right? Any other confusion? As I can say, this type variable you can specify any names for any like symbol for that variable. I believe I can even write A B C, and here also I can write A B C. Yeah, whatever. Yeah, even this is allowed.
Yeah, nothing much. Concepts are clear. The only
Yeah,
thing,
but yeah, the symbols and notations, it might
syntax
seem,
are
yeah,
quite
seem
new to me,
quite
right?
alien. Yeah, but the one thing you have to consider is if you try to implement this same permutations function in another programming language, it won't be as elegant as it looks right now, right? Because it is a recursive problem, right? And recursive problems are very expressive in functional programming languages. And in Haskell, since Haskell is a strongly typed programming language, you get type guarantees also. There are other functional programming languages also, like Lisp, Scheme, right? And the Lisp family of functional programming languages, right? And you have this Elixir and Erlang also, right? So these functional programming languages are like dynamic functional programming languages. They are similar to Python. You don't specify types during compile time when writing the code, right? The types are dynamically checked during runtime. Okay, even in that functional programming languages, you can write code like this, but here the advantage is that the code are you get type guarantees. The guarantee that you won't you the idea is that you won't get type errors in runtime. The possibility of the runtime errors are very small in Haskell compared to other functional programming languages.
I have one more doubt. So we have written the factorial function, right? And that
Yeah.
is taking really a lot of time to print the output. So can this be written in a very better optimized way, like
No,
how
no,
it
no.
is?
See, that there is no, you cannot optimize the output. If the output itself is a very long number, then what is the point of optimizing it? See, you want to print what is 10 factorial? What is 10
something
fact?
around
Let's call it. What is 10 factorial? It is a
36.
million numbers, right?
Yeah.
Three around 3.6 million numbers. So you are if you want to print 3 million numbers, you have to print 3 million numbers. What are you going to optimize there, right? That's another question. Yeah, of course. If you write this code in C, right? I mean, writing this code correctly in C itself is a huge task, right? So it won't look as simple as that we did right now.
Because
It's
what
going
I
to be
believe is writing the code in recursion um, will recompute the same things again and again,
no,
right?
no, no, no. Here it won't.
Here
Here
it will.
for permutations it won't. If you observe it carefully, here we are not. Here we are linearly subdividing the problem. Okay, so here we are not dividing the problem in half or something like that. Here we are linearly subdividing the problem, so there won't be any subproblems, common subproblems. For example, first I'm saying compute the permutations of 2, 3, and 4, and that will recursively call the computations of 3 and 4, right? So from the bottom up, we are just keep building it. Okay, so we won't have any subproblems here. Right, and Haskell compiler is itself very powerful. It does a lot of optimization. Most of the function calls it can convert it into a tail recursion. Yeah, and it has like dynamic stack allocation and so on. There are so many features baked into it. It's a very complex compiler actually. Right, we'll keep learning. So today we looked into a simple permutation problem, right? But it is not simple. But the idea is that. We got the basic understanding of how recursion and list works in Haskell, right? Soon we will solve some interesting problems. Okay, and we can delve into some complex topics in Haskell also later, right? So I think that's enough for today's